And now I have a pleasure to announce and introduce first speaker from the physics side. We have Professor Saverio Pascazio from Bari, Italy, who had a lot of nice, great contributions to quantum mechanics, quantum information, and he will tell us about quantum dynamics of quantum mechanical systems. So, Saverio, please check if you can share the screen.
Yes. Hello, Carol.
Hello, hello, Saverio.
Hello.
Buon pomeriggio.
Hello. So let me try and share the screen, or yes. I will share the presentation. Can you see it?
Yes, yes, we can. We are with you.
Okay, great. So I think if you can see the presentation only, I will just proceed like this. Or do you want me to open it up for the full screen?
Yes, yes. But so could you please make the screen a bit larger? It's almost perfect.
What about this?
Yes, better.
Okay, great. So can I proceed like this?
Yes, please go ahead.
Okay, great. So first of all, let me thank all of you for being here, and let me thank you in particular, the organizers, Carol and all the organizers for inviting me to give this talk. So since I'm the first speaker, I'll take advantage of of the fact that I'm the first speaker in order to tell you a little bit more what my personal recollections are about not only what I did together with George, but about George's contributions in general. So the title of the presentation is The Dynamics of Quantum Mechanical Systems, and this will become clear in a while as I proceed and tell you what I think about George's contribution. So we are here to celebrate the 60th anniversary of the paper on dynamical maths by George and Mathews and Rau, this paper here, in which they look for the most general dynamical law for a quantum mechanical system with a finite number of levels. Now, this is a technical paper. So let me, sorry, I get, okay. So this is a technical paper, so I will not, how can I say, go into technical details and linger with technical details. I will rather try and explain you what I think are the main ideas behind this paper and behind George's work in general. So George has contributed to a number of very interesting topics in physics during his long career. And let me start by reminding that there was a very interesting workshop, a very interesting conference a few years ago in Texas, which was entitled The Seven Science Quests. This was mentioned by Bamati before, and these are 7 of the many contributions that George gave. I don't know if these are the most important contributions, but they are certainly very important contribution to physics. So the V minus A theory, let me read it. Let's read these contributions together. The V minus A theory, which was defined by Weinberg, the key, V minus A was the key, and this was understood by George. Then symmetries, then spin statistics, then quantum optics, then the quantum Zinn effect, the theory of tachyons, and the quantum mechanics of open systems. Now, I will not try and be diplomatic here. I think there is enough material, not for 1, but for 3 Nobel Prizes here. So I have always been a little bit surprised that George's work was not recognized with a Nobel Prize. Of course, George got the Dirac Medal at the end of his career. This was an important recognition, but I think I will not try and be diplomatic. As I said, I think he would have deserved more. So now I will not, Bamati made an excellent job in describing what George's contributions have been in the last, in all these topics, but I would like to focus on this contribution, the last one, the quantum mechanics of open systems, in which, and this is a topic in which he wrote this fundamental paper together with Mathews and Rau. Now, let me give you a few references before I even start. These references are a beautiful elementary paper by Gkls and Petruccione, written a couple of years ago. Then a paper by Dagmar Bruce and Chiara Machiavello, written 15 years ago. Then there is this beautiful book which is already a milestone in quantum application by Bengtsson and Zyskowski. And then two papers I've written, one together with Beppe Marmo and the other one together with Darek Kruszynski, on the legacy of George Sudarshan and the brief history of the Gkls equation. I will not quote this paper as I proceed in my talk, but my talk is based. So I will be giving a summary of what is explained in great details in these beautiful papers. Okay, this is going to be just a little bit technical. When you describe a closed quantum system, you do this by writing a Schrodinger equation. Now, this is a milestone in the scientific literature, and it's the fundamental equation in quantum mechanics. It is not only the fundamental equation in quantum mechanics, it is the fundamental equation in quantum field theory as well. Although it looks non-relativistic, it can be given a beautiful and very elegant relativistic formulation. Now, this is the way we describe closed quantum systems. So it is a milestone because this equation has been never found wrong in all experiments so far, ranging from atomic physics, molecular physics, high energy physics, quantum statistical mechanics, and quantum information. What about open quantum systems? Now, this is a very interesting question, because if you try and describe not closed quantum system, this is very well done by the Schrodinger equation. If you try and describe open quantum systems, well, then you have to apply what is called the Kraus representation for the density matrix. The Kraus representation is what is written here in this equation. This is known in the literature as the Kraus representation. Kraus introduced this representation in 1971. Now, this is the only paper I will quote. This is a paper that I wrote with Darek, in which we were analyzing the time, the temporal evolution of these ideas behind the Kraus representation and what we call nowadays the Gkls equation. The S in Gkls is, of course, George Sudarshan. Now, when Darek and myself, we looked into the details of what had happened in history, we decided to, summarize this in a table. And this is the table just in front of you now. There was a paper written by Steinspring in 1955. Then there is a paper written by Sudarshan, Mathews and Rau in 1961. And then there is the paper written by Kraus in 1971. Then there are other very important papers. These are all milestones in the theory of open quantum systems. Now, I will not go into details, as I said before. However, I have to stress, and you should notice, that the paper by Sudarshan, the SMR paper, was published 10 years before Kraus. So why do we call this the Kraus representation and not the SMR representation, for example? Or why don't we give it another name? Now, this is a question for historian. I don't know, and I'm not entitled to, correct historical errors. But I just want to notice that the paper by SMR was published 10 years before. Yet, let me go back. We call this equation the Kraus representation. So Kraus introduced this in 1971, but there is a paper by George, Mathews and Rau that was published 10 years before. Why is that? Well, this is just one, a brief summary of this paper, the SMR paper. In equation 36, you see this is the evolution of the density matrix. Rho is the density matrix, and A is what we call nowadays a superoperator. And in equation 37, I'm sorry for being a little bit technical, this was anticipated by Carol before. There are the conditions that the superoperator A, this matrix A, should satisfy. And this condition is hermeticity, positivity, and trace preservation. So now, if you look at equation 37, you immediately ask, where is complete positivity? Because in equation 37, the notion of positivity was introduced by SMR in 1961, but the notion of complete positivity is lacking. So where is this notion? How could SMR derive the most general dynamical law for a quantum mechanical system? You know, this is just above equation 36. This is taken from the abstract of the paper. How could they derive the most general dynamical law for quantum mechanical system without being aware of the notion of complete positivity? And the answer is the following one. It was anticipated by Carol and partially by Bamati before. I mean, the notion of positivity that was, if you translate this notion in terms of another matrix, another operator B, this notion translates into the central equation there. And for this new matrix, we know that this new operator is not positive, but only block positive. So there is, the notion of positivity is not valid. This operator is simply block positive. So you see, this is the issue. This is the point I would try to make. SMR are deriving the most general dynamical law. The most general dynamical law is correctly formulated. So this is anticipating the Kraus representation 10 years before. Yet it lacks the notion of complete positivity. Why is that so? Because the matrix that they are using is not positive, it is only block positive. So my point of view, and I think I share this point of view together with Darek Kushinsky, is that this error, I put the word error within quotes. In physics, let me say physics is not mathematics. In mathematics, we have errors. In physics, sometimes we know what the final result is, or we know where we want to get, or we know what we know. We have expectations, and these expectations are based on physical, how can I don't want to say on feelings, but on some physical sense or prejudice or whatever. And so you cannot talk about an error, strictly speaking. This is probably an error from the mathematical point of view. But although the derivation contains a gap, the final result is correct. The law is correctly formulated. So they got the right equation for the dynamical maps without complete positivity. If I think of this, I still find this astonishing in a way. And it is clear to me, and probably to Darek also, that this remarkable SMR paper was written too early. 10 years too early, and the community was not prepared to grasp its elegance and predictive power. The equation was correctly formulated, the dynamical law was interpreted in the right way. However, the matrix was only block positive, it was not positive. Okay, so it is the right result, probably not framed in a perfectly consistent mathematical framework. So the notion of complete positivity was lacking at that time. I'm sure that Sudarshan, SMR were not aware of it, yet they formulated the correct physical law. If you take the Markovian limit, this is what we call the Gorini, Kosakowski, Limrad, Sudarshan equation. You get an equation that is a milestone in contemporary physics. It describes open quantum systems in the Markovian approximation. This is used every day nowadays when you try and describe open systems, you know, in the weak coupling limit. So this Gkls equation derives from the SMR framework if you take a certain limit. So it is a fundamental equation in a limit, and it can be derived by the equation that I wrote before. Where is the problem? Well, in a way, when I was preparing this talk, if you ask me, is there a problem? I think there is no problem. There is no problem. It's clear what happened. The physical law was correctly formulated, but it was formulated 10 years too early, in my opinion. However, one should be aware of the following fact. We should be aware that SMR first and Gkls later were looking for a characterization. Nowadays, this seems very obvious to everybody. However, at those times, it was not even obvious that the characterization of the dynamics of open system was necessary. Let me be a little bit more precise. We all know that for closed quantum systems, we have to write a Schrodinger equation. And we take this as a paradigm of closed quantum system, quantum field theory, quantum mechanics, and so on. Now, you consider an open quantum system, and at those times, 40, 50 years ago, people would write equations, and these equations were correct. However, these equations were, in a sense, people were doing engineering. They were taking a closed quantum system, they were embedding it in a larger system, they would take the weak coupling limit, and they would derive what we call nowadays the master equation, or the Gkls equation. So it is engineering. So you derive an equation because you need it for your purposes, because you have to describe the physics of lasers, the physics of an atom in the radiation field, whatever. You have an objective and you solve your problem. And this solution is specific, it pertains to your problem. It is not obvious that this needs a characterization. It's not obvious that an open quantum system should have an equation and that this equation should obey some physical principles in itself. This is, in my opinion, what SMR first and Gkls understood later, that there was the need to characterize. Nowadays, we take this need for granted, but it is by no means obvious. And this was certainly not obvious 40 or 50 years ago, in my opinion. It is difficult to judge papers that are 50 years old or 50 or 60 years old with the knowledge we've acquired during the last 40 years. We tend to take things for granted, and they are not obvious, in my opinion, by any means. Okay, so summarizing, why did I choose to talk the dynamics of quantum mechanical systems? Because for closed quantum system, we have the Schrodinger equation, and for open quantum system, if you try and characterize them, you have an equation that stands on the same level. And this is, maybe we should call this Kraus Sudarshan representation, or maybe KSMR representation, as we refer to the Gkls equation. It should stand on the same level. It is a fundamental way to describe the dynamics of open quantum systems. Let me add that there are no closed quantum systems. The idea of a closed quantum system is an idealization. There is nothing like a closed quantum system in real life. All systems are open. So we need to characterize them. And it's not surprising, but I still find it very remarkable that the characterization of the dynamics of open quantum system is possible. This idea is very prolific. The idea that you need to characterize open quantum system. First of all, it leads you to the concept of CPTP maps. It helps you to understand entanglement, to understand partial transposition, to understand time reversal. This was the point of the papers that I quoted before and that I'm not quoting now. And also something very philosophical. This is typical of George's legacy. He would start from physics principles, very practical dynamical laws, and then he would go back to philosophy and he would ask you, what is an isolated system? For instance, I ask you, does isolated also mean to be correlation free? Nowadays, we know that this is not obvious. And indeed, this is what a CPTP map is written for. It is written because it must protect, in a sense, the dynamical law from the very possibility that the system you are investigating is correlated with the outside world. So correlated does not mean isolated. Nowadays, once again, we take this for granted, but try and ask one of your students, is an isolated system correlated? Chances are that they will say, no, it's not correlated, it's isolated. But the fact that the system is isolated here in this room, I'm talking from Italy, some of you are in Poland or in India or in the United States or in South Africa, the fact that we make an experiment here in an isolated, we isolate our system, does not mean that our system was not correlated to something else yesterday evening, for example, or 1 week before. Or it doesn't mean that our system is not correlated with some electrons that now are on Andromeda or a different star. So correlation is something that can survive isolation. This is a lesson that was very clear to George, very, very clear to George. Okay, I would like to end this note with one of my the small things that I've done in collaboration with George. One was on the quantum gene effect. I love this picture because I was much younger than I am now. This is an old picture at the Solvay conference, and you can clearly see a quantum gene effect because the speaker, myself at the center, cannot move like in the quantum gene effect because it's being closely observed by Misra on the right on the picture and Sudarshan on the left. Also, let me finish with a couple of anecdotes. One, I wrote a paper and I decided to finish with anecdotes. One, I would like to read it together with you. It's something that happens in Naples 20 years ago. I was in Naples with Paolo Facchi, certainly my closest collaboration, and Beppe Marmo was there together with George and Vittorio Gorini. And we were talking about the quantum gene effect. And that some of us were at the blackboard, and someone said, the Hamiltonian is self-adjoint. And after a split second, George replied, why should it be self-adjoint? Is it not sufficient that the Hamiltonian be symmetric? Now, this was, of course, we published a paper out of that discussion, but this is not the point. The point is that George would never take a postulate for granted. You can say, you are at the blackboard, you are 30, 40 years younger, you say the Hamiltonian is self-adjoint, and they will just say, why are you assuming that the Hamiltonian is self-adjoint? Maybe in this setting, a symmetric Hamiltonian would be enough. Again, this is a question that is still in my memory, because every time one of my students starts at the blackboard and says, the Hamiltonian is self-adjoint, the student doesn't know, but in my mind, I have this question by George, which goes back more than 20 years. I have an anecdote with George and Bamati, but for respect to Bamati, I will not go to this anecdote. I would rather go to another anecdote, to another question asked by George in 2014. We invited to give a public talk at the University of Bari, and a lot of people were present, maybe more than 200 people. The main hall of the physics department was full. And there were many questions at the end of the seminar. And someone, I don't remember exactly who, but he was a young person, either a student or a postdoc. He asked, Professor Sudarshan, what do you think about the discovery of the Higgs particle that had been announced a couple of years before? And George said, young man, I would not worry about Higgs. I would rather ask, why the muon? Now, this is something typical of George. He is not by any means dismissing the importance of Higgs, but he's telling the young student, look, worry about the muon before, because it's not clear why a muon should be like an electron in quantum field theory, in the standard model. Think about the muon, and then let's worry about the muon, and then let's worry about Higgs. These precepts are totally lost in high energy physics nowadays, totally lost. These are Bamati and George in Italy. I was very happy to welcome them. I'm very happy to close with this picture. A lot of people are there. Manco, both wife and husband, and Elisa Colessi and Beppe Marmo, and then a number of other collaborators. I'm very happy to, I was very happy to organize this small symposium. And this is the way I would like to remember George and to greet Bamati today. So thank you very much for your kind attention.
Thank you very much, Saverio. Great talk. And we have now a few minutes for discussion. Are there any questions? You can write them if you wish on chat, or perhaps somebody would like to start. So Francesco, I see your hand. Francesco, would you like to pose a question or make a comment?
Yeah, no, sorry, Carol. I made a mistake. I wanted to clap and I clicked on the wrong.
Okay.
on the
Okay.
wrong
So
symbol. But since I'm
perhaps
here,
you have some questions or comments.
Let me use the opportunity to thank Saverio very much for a very nice overview and going back to the historical origins and the context of the famous paper that we want to celebrate in this today. So thank you very much, Saverio. It was really very nice. Thank you.
Thank you for inviting me, Francesco. It was my great pleasure and the honor.
Great.
Absolute pleasure. Yeah. I was hoping that we could do this workshop in South Africa, but with COVID, it was not possible. Maybe we will do another one in 10 years.
Yes.
I understand. Looking forward.
Yes. Perhaps we'll meet somewhere on site. Now we are still together online. So Usha Devi would like to pose a question. I see the.
This is a thank you.
Please.
This block positivity of the B matrix, basically. So the B matrix, if we had only restricted to block positivity and not complete positivity, has that been explored or any comments on that? Not the complete positivity, but only restrict to block positivity. Has that been investigated by anybody following SMR paper? This is my question, if it makes sense.
Yeah, it does make sense. It does make sense. Yeah, just 1 minute to respond. Thank you for the question.
It is something like saying, sorry, it is something like saying I have a positive matrix, then I would only take determinant positive and forget about everything else. It is like that if I had only restricted to block positivity and ignored everything else, would I have gone somewhere? Like just starting from the SMR paper. This is just a question that I got. So I wanted to ask you.
Yeah, I understand. Can you still see the screen that I'm sharing, the presentation?
Yes, we can.
Yeah. So first of all, there are these 3 beautiful papers by Gkls and Petruccione, by Bruce and Machiavello, and by Bengtson and Zyskowski. So go in particular, for example, to the book by Bengtson and Zyskowski to understand the notion of block positivity. So it is very clear that there is a clear distinction between positive and block positivity. Nowadays, we use this exactly to characterize entanglement. So there are applications. If the matrix is, for instance, block positive but not positive, you can use it to characterize entanglement at a distance. So not only we know how to use it, but the notion in itself is telling us something about the physics of the correlations that your system might have outside your, how can I say, your laboratory. So it is a very useful notion for a number of very important reasons. It is being used, by which maybe something else will emerge if we do more research during the next 10 or 15 years. I don't know. I would not be surprised if something new would emerge. This is already used. Please refer to these 3 papers, and there are a lot of applications. How to use the notion of positivity versus complete positivity versus block positivities. It is a very interesting notion. I mean, it's very clear to me what it means from the physical point of view, but I would not be surprised if some young person would come up with a novel application in a few years or in a few months. I don't know. Thank you. It makes a lot of sense.
Thank you. So now let us ask Fabio, first of Benatti, to ask a question. Hello, Fabio.
Hello, Carol. Thank you, Saverio, for the nice talk. I want just to make a comment related also to the previous question. And the comment is about the difficulty in those years, early 60s, to appreciate the content of the paper and the lack of complete positivity and the notion itself of complete positivity. I mean, complete positivity to my mind is the mathematical facet of entanglement. The 2 things are closely related. And in those years, in the early 60s, entanglement was either an unknown companion or a dangerous companion, something to be put under the carpet. So this is also partly an explanation of the difficulty in appreciating the content of that paper. About the question of block positivity, I would say that block positivity, in some sense, exactly because reveals entanglement, so shows whether a state is entangled or not, the block positivity of maps, at the same time makes these maps non-physical, because they would kind of behave wrongly on entangled states. And another comment is, nowadays everybody takes a complete positivity for granted. I would say almost everybody. There are a lot of, say, attitudes that are trying to purport that complete positivity is a constraint of mathematical origin, not really physical, so physically unneeded, a physical constraint which could be overcome in order to attain more general and more satisfactory from certain points of view dynamics.
Thank you, Fabio. Other further questions or comments? Dariusz, yes.
So Saverio, congratulations for a great presentation. What is very puzzling for me for many years is why Gorini, Kosakowski, and Sudarshan did not cite Sudarshan, Mathews, and Rau paper.
Good question.
So if I
this
can
is really very puzzling.
Yeah. So can I comment briefly? So first of all,
sure.
I would like to thank both Fabio and Darek. I think Fabio is the person with whom I have discussed complete positivity most of all persons that I've met in my academic life. So in a sense, I completely share Fabio's point of view, maybe because I discussed with him too much. Complete positivity is not a mathematical notion. There is something physical that is very clear to me, and I agree, not everybody agree with this. There is still some people who think that you can write more general evolutions. It's okay. We live in free countries, so this is perfectly fine. But I completely share Fabio's point of view that complete positivity is a necessity if you want to correctly describe the evolution under when in the presence of correlations. If I can make a philosophical comment that I've never had the fortune, the opportunity to discuss with George, when you write a differential equation, you write a differential equation because you implicitly assume that you can write all possible initial conditions. So you write F equal ma because you know that whatever happens to your particle, however you start, you can write F equal ma and follow the evolution of the classical system. Now we assume implicitly that the same is true in quantum mechanics. Indeed, it is true in the Schrodinger equation. There is a difficulty of preparing the initial state, but we assume this to be valid. Now ask yourself, is this valid for open quantum systems? If the evolution is positive, no. You are not allowed the evolution is not valid for any possible initial state. So this is the point. We are writing an evolution equation, differential equation, but this is not valid for all possible initial conditions. What Gkls, SMR, and other understood on physical grounds is that if you want an evolution and you want to be able to write this evolution for all possible initial conditions, you need complete positivity. This is the lesson. I have no way out. Maybe I'm getting old enough, you know, I am unable to find a way out, but this is the lesson I've learned. I'm puzzled like Darek. So this is not an answer to Fabio, but a remark. As for Darek, I also wonder, why did they not cite the SMR paper? This is a mystery in the mystery. I don't know. We should ask George. That's the only way to understand. I'm also very puzzled.
Thanks for all the remarks. Thanks, Saverio, for such a nice talk. Let us thank the speakers